Good day, the topic is Fundamentals of Fluid Flow. To start, flow pattern or flow field refers to lines constructed to show the direction of flow. For example, in the figure, water from a tank exits the opening as shown. It helps us in distinguishing different types of flow, usually expressed in the velocity as s all over t, where s is the distance traveled and t is the time of travel. On the other hand, path line is the path of a particle as it moves through a flow field. The streamline is the line generated by a tracer fluid, while stream tubes are bundle of path lines. For the different terms for types of flow, first, the uniform and non-uniform flow. For uniform flow, velocity does not change along a fluid path, or fluid paths are straight and parallel, while non-uniform flow has velocity changes along a fluid path. Second is steady and unsteady flow. For steady flow, the velocity at a given point on a fluid path does not change with time, while the unsteady flow, the velocity at a given point on a fluid path would be increasing or decreasing with time. Third is the laminar and turbulent flow. For laminar flow, it happens when a well-ordered flow in which adjacent fluid layers move smoothly with respect to each other. While for turbulent flow, it happens when an unsteady flow characterized by intense cross-stream mixing. And on the other hand, the term transitional flow is the critical flow, which is in between laminar or the transition between laminar and turbulent flow. Fourth is the dimensional flows. For one-dimensional flow in a circular duct, velocity is uniform and depends only on one direction, which is the radius. For two-dimensional flow in a rectangular duct, flow depends on x and y dimensions. For three-dimensional flow in a diverging rectangular duct, flow depends on x, y, and z dimensions. Fifth is compressible and non-compressible flow. Compressible flow is flow that undergo a notable variation in density with trending pressure, while non-compressible flow refers to the fluid flow in which the fluid's density is constant. Sixth is rotational and irrotational flow. For rotational flow, fluid particles, apart from moving along the flow, rotate about its own axis with some angular velocity, while irrotational flow refers to fluid particles, while flowing, do not rotate about its own axis. Next is for the rate of flow or discharge, presented with capital Q. The volume of fluid passing a cross-section of a stream in a unit time. And in formula, Q is equal to the volume V over time T. For its units, it is either cubic meter per second, cubic foot or cubic feet per second, or GPM, the gallons per minute. Another is an analysis with equal velocities at all points in the cross-section of a stream. Thus, in formula, Q is equal to area A times velocity V. Take note that area must be perpendicular to the flow or this velocity V. For continuous flow, it happens when, at any instant, the number of particles passing even or every cross-section of the stream is the same. For this condition, the continuity equations are the following. For flow rate, Q is equal to A sub 1 times V sub 1 equal to A sub 2 times V sub 2. For mass flow rate, all are multiplied with density, while for weight flow rate, all are multiplied with unit weight. Take note that velocity at shorter area is larger than the velocity at greater area. So let's take now our sample problems. For problem number 1, compute the discharge of water through a 3 inches diameter pipe if the mean velocity of flow is 8.5 feet per second. The summary of given D is equal to 3 inches, velocity V is 8.5 feet per second. The required is discharge Q. For the solution, the discharge Q is equal to A times V. Substitute for area, the circular section pipe that is pi all over 4 times the diameter 3 inches and convert to corresponding foot and raise to 2. Then the velocity V as 8.5 feet per second. Therefore, for Q, it is equal to 0.417 cubic foot per second. For sample problem number 2, a pipeline consists of successive lengths of 15 inches, 12 inches, and 10 inches pipe with a continuous flow through the line of 9 cubic feet per second of water. Compute the velocity in each pipe. For continuity, Q is equal to A sub 1 times V sub 1 equal to A sub 2 times V sub 2 and equal to A sub 3 times V sub 3. That is 9 CFS or cubic feet per second. Thus, for velocity of pipe 1, the V1 is equal to the uniform Q all over A sub 1. Substitute Q as 9 cubic feet per second, and for area, that is pi all over 4, multiply to 15 inches, convert to feet, and raise to 2. Therefore, V1 is equal to 7.334 feet per second. For velocity of pipe 2, V2 is equal to the uniform Q all over A2. Substitute Q as 9 cubic feet per second, and for area, that is pi all over 4, times the diameter, that is 12 inches, convert to 1 foot and raise to 2. Then, V2 is 11.459 feet per second. For velocity of pipe 3, V3 is equal to the uniform Q all over A3. Substitute Q as 9 feet per second, and for area, that is pi all over 4, times the diameter 10 inches and convert to foot and raise to 2. Thus, V3 is 16.501 feet per second. The sample problem shows that smaller area has greater velocity of flow for continuous flow system. Next, for sample problem number 3, the velocity at section A to A is 18 feet per second, and the vertical depth Y at the same section is 4 feet. If the width of the channel is 30 feet, what is the discharge in cubic feet per second or CFS? For discharge Q is equal to A times V. For cross-sectional area, take note that consider the perpendicular area to the flow. Thus, A is equal to Y prime times W, or the width of the channel. For Y prime, let us consider cosine of 30 degrees equal to the adjacent, that is Y prime, over hypotenuse Y. Rearrange and substitute Y as 4 feet. Therefore, Y prime is 3.464 feet. Substitute in equation of A together with the width of channel that is 30 feet. Therefore, A is 103.923 square feet. In equation of Q with V that is 18 feet per second, Q is equal to 1,870.615 cubic feet per second. And for our problem number 4, what is the velocity of the flow of water in leg B of the T shown in the figure? The requirement is the velocity at B section. For the solution, assume continuous and steady flow. The flow at A is equal to the sum of the flows at B and C. Substitute the formula of Q, that is area times velocity, and rearrange. For A, the area is pi all over 4 times 4 meter raised to 2, the diameter, times the velocity that is 6 meters per second, minus for C, the area is pi all over 4 times the diameter 2 meters raised to 2, times velocity that is 4 meters per second. Then divide to area at B, that is pi all over 4 times the diameter 4 meters raised to 2. Therefore, V at B is equal to 5 meters per second. Now let us consider the principle of the Bernoulli energy equation, or BEE. According to Daniel Bernoulli, for the stream flowing steadily without friction, the total energy contained in a given mass is the same at any point in its path of flow. Another is, BEE is concerned with conservation of kinetic, potential, and flow energies of a fluid stream and their conversion to each other. Energy is the ability to do work. For the case of fluid, it is the ability to continuously flow. The picture presents the relationship of potential and kinetic energy, where potential energy is associated to mass and position, while kinetic energy is attributed to mass and speed. The diagram therefore shows the components of kinetic and potential energy. For kinetic energy, KE is equal to the weight W times the velocity raised to 2 all over 2 times the gravitational acceleration. For potential energy, we have due to elevation head, that is PE sub E is equal to the weight times the depth Z or height Z. And due to pressure head, PE sub P is equal to the weight W times the pressure P all over the unit weight of the fluid. Therefore, for the total energy, we will sum the effect of kinetic and potential energy. But considering weight of unity, the total energy is V raised to 2 all over 2G, the velocity head, plus P all over gamma, the pressure head, and Z, the elevation head. Neglecting friction, the total amount of energy per unit weight is the same at every point in the path of flow. Therefore, the sum of velocity, pressure, and elevation head at point 1 is equal to the sum of velocity, pressure, and elevation head at point 2. So let's have our sample problems. For problem number 1, piezometric tubes are tapped into a venturi section as shown in the figure. The liquid is incompressible. The upstream piezometric head is 1 meter and the piezometric head at the throat is 0.5 meter. The velocity in the throat section is twice large as in the approach section. Find the velocity in the throat section, or that is V sub 2. Consider the relationship of the total energy at points 1 and 2. And take note that for the given, we have the relationship of the velocities, that is for V2, it is equal to twice of V1. Again, For smaller area, the velocity is greater than that of the larger area. So let's proceed. The sum of velocity, pressure, and elevation head at point 1 is equal to the sum of velocity, pressure, and elevation head at point 2. But according to the problem, again, V2 is equal to twice of V1. An elevation head as part of the pressure head. Therefore, simplify the equation, transpose terms with unknown V2 at the left. Simplify the equation and get the LCD of the left side of the equation, that is 4. Then cross multiply 3/4 to the other side. Therefore, for V sub 2, it is equal to the root of 8 all over 3 times G times 0.5 meter. Substitute the gravitational pull, that is 9.81 meters per square second. Therefore, the velocity at point 2 is 3.617 meters per second. For sample problem number 2, a water jet issues vertically from a nozzle, as shown. The water velocity as it exits the nozzle is 20 feet per second. Calculate how high h the jet will rise. To start, assign points at nozzle as point 1 and at the highest point of the vertical jet as point 2. Consider the relationship of the total energy at points 1 and 2. The sum of velocity, pressure, and elevation heads at point 1, and it is equal to the sum of velocity, pressure, and elevation heads at point 2. For the assumptions, first, pressure or gauge pressures exposed to the atmosphere are 0. Thus, P1 and P2 are equal to 0. Next, the reference or datum is at point 1. Therefore, Z1 is equal to 0 and Z sub 2 is h. Last is the velocity at the end of jet or point 2 is 0. From physics, if the body thrown vertically reach its maximum height, the velocity of that body is 0. Updating the equation, thus, h is equal to v sub 1 raised to 2 all over 2g. Substitute v1 as 20 feet per second and the gravitational pull as 32.2 feet per square second. Therefore, h is 6.211 feet. Now, let us discuss lost energy or head loss, represented with capital HL. It may occur as a result of friction between fluid particles as they rub against each other. As shown in the figure below, the particles at the mid-zone is moving freely, but the particles adhesive to the channel wall is almost stationary due to friction. Fluids in motion suffer a loss of energy through friction. Assume points 1 and 2 for the figure shown. The energy at point 1 is greater than the energy at point 2. To make BEE balance, add HL value to E2 or the total energy at point 2. Thus, the updated BEE with head loss is this equation with corresponding head loss value from points 1 to 2. Again, added at point 2 for balance condition. And for addition of pump, energy is added between the 2 points. Thus, we will consider H sub P as the increase in head due to pump, added at the left side of the equation, while energy is lost or given up between the 2 points due to turbine. Thus, we will consider H sub T as an addition to head loss at the right side of the equation. One purpose of turbine is for generation of electricity. So let us now consider the visual representations of energy, the grid lines. First is EGL, or energy grid line. So it is a line that indicates the total energy head. Again, total energy, the combined velocity, pressure, and elevation heads. The second is HGL, or hydraulic grid line. It only shows piezometric head, the sum of pressure and elevation head. Again, for HGL, we will consider only pressure and elevation head. The velocity head is not included. We have sample figures below. At the left, it is due to pump. There is rise in EGL and HGL. While at the right, due to turbine, there is drop in EGL and HGL. On the other hand, for power, capital P, it is the power given by pump or delivered by a turbine. In formula, P is equal to unit weight, gamma, times discharge, Q, times head of pump or turbine, that is H, either HP or H sub T. Unit of P is either in watts or horsepower. Next is the efficiency represented with Greek letter eta. It is the accounted energy loss due to mechanical friction, viscous dissipation, and leakage, and defined as the ratio of power input to power output. In formula, eta is equal to P sub output all over P sub input. So let's take now our sample problems. So for problem number 1, the horizontal pipe carries water for thermal power plant from a reservoir as shown. The head loss in the pipe is 0.02 times L all over D times V raised to 2 all over 2G, where L is length of the pipe from reservoir to point 2, D is the pipe diameter, V is the mean velocity of flow in the pipe, and if the pipe diameter is 20 centimeters and the rate of flow is 0.06 cubic meter per second, what's the pressure in the pipe at a length of 2,000 meters? First is the BEE equation for points 1 and 2 with head loss. For assumptions, pressure exposed to atmosphere is 0. Thus, P1 is 0. Next, stagnant velocity is 0. Thus, V sub 1 is 0. Update the equation and rearrange for unknown P sub 2. Then, let us determine for velocity at pipe 2, V sub 2 is equal to Q all over A sub 2. Substitute Q as 0.06 cubic meter per second and area as pi all over 4 times the diameter as 0.2 meter raised to 2. Thus, V sub 2 is 1.91 meters per second and is equal to the velocity of the pipe. For head loss between points 1 and 2, substitute L as 2,000 meters, D as 0.2 meter, velocity of pipe determined earlier as 1.91 meters per second, and the gravitational pull as 9.81 meters per square second. Thus, the head loss between points 1 and 2 is 37.182 meters. Substitute gamma in our equation of P2 as 9.81 kilonewtons per cubic meter, Z1 as 100 meters, V sub 2 as 1.91 meters per second, the G or the gravitational pull as 9.81 meters per square second, Z sub 2 as 20 meters, and the head loss as 37.182 meters. Therefore, the pressure at point 2 is about 418.220 kilonewtons per square meter or kilopascals. And for our sample problem number 2, a pipe 50 centimeters in diameter carries water at a rate of 0.5 cubic meter per second. A pump in the pipe is used to move the water from an elevation of 30 meters to 40 meters. The pressure at section 1 is 70 kilopascals gauge, and the pressure at section 2 is 350 kilopascals gauge. What power in kilowatts and in horsepower must be supplied to the flow by the pump? Assume head loss as 3 meters of water. So first part of the solution is for our BE equation for points 1 and 2. Rearrange for unknown H sub P. For V1 and V2, we have equal discharge Q and area A, thus equal velocity. Therefore, we can cancel the impact of velocity head. Thus, the V2 raised to 2 all over 2g minus V1 raised to 2 all over 2g is now equal to 0. Substitute in equation P2 as 350 kilopascals, P1 as 70 kilopascals, unit weight of water as 9.81 kilonewtons per cubic meter, Z2 as 40 meters, Z1 as 30 meters, and the head loss between points 1 and 2 as 3 meters. Therefore, the required height for the pump is 41, or the required energy for that pump is 41.542 meters. For power needed by the pump, it is equal to the unit weight times the discharge times the energy head of the pump. Substitute gamma as 9.81 kilonewtons per cubic meter, the discharge Q as 0.5 cubic meter per second, and HP as 41.542 meters. Thus, the power needed is 203.765 kilonewtons meter per second. For conversions, for every 1 kilonewton meter per second, it is equal to 1 kilowatt, and 1 horsepower is 0.746 kilowatt. Therefore, for this power, convert to the value kilowatt, the power needed is about 203.765 kilowatts. And convert to horsepower, the power needed is about 273.143 horsepower. Okay, so that's it for the topic Fundamentals of Fluid Flow. Take care and God bless.